Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. In our last episode, we walked through what neutron stars actually are, the crushed cores of dead stars spinning hundreds of times per second. With magnetic fields a trillion times stronger than Earth's, superfluid interiors whose physics were still working out, and timing precision good enough to detect gravitational waves rippling across the galaxy. We ended on two neutron stars spiraling toward each other in an inevitable collision. Today, we're going to find out what happens when they hit, and why that collision is directly responsible for every piece of gold and platinum that has ever existed anywhere in the universe. Then we're getting into the theories, from legitimate scientific debates about neutron star physics, to the stranger claims about what these objects might actually represent. Let's get into it. When two neutron stars that have been spiraling toward each other for millions of years finally collide, the result is an event called a kilonova, an explosion roughly 1,000 times more energetic than a typical nova, but significantly less energetic than a supernova, with a distinctive appearance and an extraordinary chemical signature. The collision happens at a significant fraction of the speed of light. The two neutron stars, each containing more mass than the Sun compressed into a sphere 12 miles across, smash into each other and undergo one of the most extreme physical processes in the universe. A process called rapid neutron capture, or the R process, in which atomic nuclei are bombarded with neutrons so rapidly that they absorb them faster than they can decay, building up into heavier and heavier elements in a fraction of a second. This R process is the only known mechanism capable of producing elements heavier than iron in significant quantities. Every element on the periodic table, heavier than iron, gold, platinum, silver, uranium, lead, iodine, and dozens of others, requires the R process to form, because stellar fusion simply can't produce enough energy to build nuclei this heavy under normal conditions. The neutron-star collision provides both the neutrons needed and the extreme conditions required for the R process to run, forging heavy elements in enormous quantities and then ejecting them into space in the kilonova explosion. Like, subscribe, and hype the video, because in 2017 we watched one of these events happen in real time for the first time in history. On August 17, 2017, the LIGO and Virgo gravitational wave detectors simultaneously detected a gravitational wave signal from two merging neutron stars approximately 130 million light-years away. Unlike previous gravitational wave detections from merging black holes, which produce no light, a neutron-star merger was expected to produce an electromagnetic counterpart, visible light, X-rays, gamma rays, and infrared radiation, that could be detected by conventional telescopes. Within hours of the gravitational wave alert going out, roughly 70 space and ground-based observatories around the world were pointing at the same location in the sky, in the galaxy NGC 4993. A new point of light appeared, a kilonova, exactly where the gravitational wave signal had localized the merger. Over the following days and weeks, the kilonova was observed across the full electromagnetic spectrum as it evolved and faded. Spectroscopic analysis of the kilonova's light, breaking it into its component wavelengths to identify the chemical fingerprints of specific elements, detected strontium definitively, and found signatures consistent with a range of other R process elements, including gold and platinum. For the first time in history, scientists had directly observed heavy elements being synthesized in real time during a neutron-star merger, confirming what had been theorized for decades, that these collisions are the primary source of the heaviest elements in the universe. The gold in every wedding ring ever made, the platinum in every catalytic converter, the iodine in the human body, all of it traces back to events like the one we watched in NGC 4993 in August of 2017. A subset of neutron stars takes the already extreme properties of these objects to another level entirely. Magnetars are neutron stars with magnetic fields roughly 1,000 times stronger than even typical neutron stars. fields so intense that they represent the strongest magnetic fields known to exist anywhere in the universe. The magnetic field of a magnetar is strong enough to distort the electron clouds around atoms, changing the fundamental chemistry of matter in the star's vicinity. At very close range, within a few hundred kilometers, a magnetar's field would be strong enough to affect the quantum mechanical behavior of atoms in the human body, disrupting the molecular bonds that hold biological tissue together. The intensity of these fields is genuinely beyond any laboratory analogy. When a magnetar's crust cracks under the stress of its own magnetic field, a starquake, the energy released can be extraordinary. In December 2004, a magnetar called SGR 1806-20, located roughly 50,000 light-years from Earth, underwent a giant flare that released more energy in 0.1 seconds than the Sun emits in 250,000 years. The burst was so intense that despite originating 50,000 light-years away, halfway across the galaxy, it briefly disturbed Earth's ionosphere, the upper layer of our atmosphere, measurably brightening it. It remains the most energetic extrasolar event ever recorded by instruments on or near Earth. Like, subscribe and hype the video. And now let's get into the stranger claims surrounding these objects. The genuinely unknown aspects of neutron star interiors, particularly their cores, have generated a range of theoretical proposals, from scientifically mainstream alternative models to considerably more speculative ideas, and it's worth being clear about where each one sits. The most scientifically credible alternative to the standard neutron star model involves quark stars, objects that form when neutron degeneracy pressure fails at the very center of a neutron star, and the neutrons themselves dissolve into their constituent quarks, forming a stable configuration of quark matter. Several observed compact objects have properties that are difficult to explain within standard neutron star models, but could be consistent with quark stars. This is a legitimate, published scientific hypothesis under active investigation. A related proposal involves strange matter, a hypothetical form of matter composed of roughly equal numbers of up, down, and strange quarks, which some theoretical models suggest might be the true ground state of matter, more stable than even atomic nuclei under extreme conditions. A neutron star made of strange matter, called a strange star, would have subtly different observable properties from a conventional neutron star, and distinguishing between the two observationally is an active research goal. Moving further from the mainstream, some theorists have proposed that neutron star cores might contain Bose-Einstein condensates of pions or kaons, or crystalline phases of quark matter, or other exotic states that represent genuinely new physics. These proposals are scientifically published but more speculative, and distinguishing between them observationally requires measurements of neutron star masses and radii with precision that current instruments are only beginning to approach. So here's where neutron star science actually stands. These objects are among the most thoroughly studied extreme environments in astrophysics, not despite being impossibly dense and exotic, but because their observable properties, particularly their pulse timing and their gravitational wave signatures, provide windows into physics that can't be studied any other way. We know that neutron stars produce the heavy elements. The 2017 Kilonova observation confirmed that directly with spectroscopic evidence. We know that millisecond pulsars are among the universe's most precise natural clocks, precise enough to detect gravitational waves echoing across the galaxy. We know that magnetars produce the most energetic events in the observable universe after gamma-ray bursts, and that a single starquake from one of them can disturb Earth's atmosphere from 50,000 light-years away. What we don't know, what the equations don't yet tell us clearly enough to distinguish between observationally, is exactly what state matter is in at the centers of these objects. That question is being actively pursued with current and next-generation X-ray telescopes, gravitational wave detectors, and radio arrays that are already in operation. The answer, when it comes, will either confirm our current models or reveal new physics hiding in the densest solid objects in the universe. Neutron stars are where the universe stores its most extreme physics and where it manufactures its most precious elements. The gold in your rings, the platinum in your electronics, the iodine in your body, all of it was forged in a neutron star collision somewhere in the galaxy. Billions of years before Earth existed, scattered into space in a kilonova explosion, and eventually incorporated into the cloud of gas and dust that collapsed to form our solar system. We are not just made of star stuff, as Carl Sagan famously said. We are made of neutron star stuff, forged in the most violent collisions in the universe, carried across the galaxy, and eventually assembled, atom by atom, into everything you can see and touch. If you've made it through both episodes, let me know in the comments what you find most extraordinary about neutron stars. Like, subscribe, and hype the video, and I'll see you in the next one.